This video is going to take the graphs obtained from video analysis of a dog sliding across the floor and slowing down, and talking you through how to interpret those graphs and obtain variable information from those graphs. So I have a picture of this. I can show it to you so you can see what the video is. Okay, here we go. Muddy's going to come sliding across the floor, and right there he stopped. So we're going to look at the motion from when he's sliding. We don't want anything that's bouncing or flying through the air, so we got to capture the first frame where we collect data to be when it's actually sliding and slowing down, or whatever motion is that we're trying to focus on. You get a lot of before and after parts of the video where it's not the motion that you were focusing on. So after tilting the line of motion so that it lines along the way the dog is moving and plotting all the points, I kind of put a picture here so you can see it. I obtained two graphs, a position versus time graph and a velocity versus time graph, which is here. So we're going to look at the position time graph first. Now, although this is the same graph, this one has the quadratic regression model in it. This one is without that. They're the same graph otherwise. I just did that so we can focus on one that doesn't have the regression and see what we can get, and one that does and see what we can get additionally there. So looking at the one left first, without doing any kind of curve fit, there's always a few things I can do, right? And that's going to be, to get values, I can always look at the x and y axes. That would be like y-intercepts, the final y value, the final x value, domains, ranges, that sort of thing. So in doing that, I'm looking at the range and the domain. Okay, so the range goes from 0, this would be like x naught, right, my beginning x value, to my final x value, x of 2.7. So the change in this is my delta x, which means that delta x is equal to 2.7 meters. And I got that as the range on the y-axis. That's how you label how you got this value, which is a really important step. The domain, which is from 0 to 1.8, so basically this final value, is my time. Okay, so this would be then, I found the variable time is equal to 1.8 seconds by looking at the final x-axis value on the time axis, which is the same as domain on the x-axis, right? This doesn't have a slope. If I scroll up, we could also look at the steepness or slope and also area potentially to get variables. Unfortunately here there's not a slope. I can't just go like, hey, there's the slope, because this is a quadratic, right? So that would mean that this does not have a constant slope. I can look at this and say that this might be 0, right, as a steepness, but without knowing for sure, I can't really do that with any certainty. So what I'm going to do now is switch over to, let's say I was able to run a regression model on the data, and I were to pick quadratic since this is a parabola. It's going to give me the mathematical model that I can fill in, right, of 0.6 right here, 2.6 right here, and 0 right here. But in our experiment, we already interpreted these variables, and that's how we created the equation that we have, right? That's 1/2 the acceleration times t squared plus v naught t, and then this would be the starting position, right? It's your x naught, just like we had in the other one. We often then would subtract this, knowing that x minus x naught is the same thing as delta x, and that would just get rid of this term. That's how our final equation ended up. So the idea is, if I know that this coefficient capital A is equal to 1/2 the acceleration, well then I can simply double this, right? Meaning that this value here is 1/2 the acceleration, right? And then this value here is v naught. And this value here is x naught. So I can directly interpret those. That would mean that I can figure out things like acceleration, right? If this is half the acceleration, then that would be negative 1.2 meters per second squared, right? And I can get that from the regression model. Since I labeled it here, that would count, right? Because I labeled it on the regression model. Okay, so you don't have to use these parentheses if you can label it directly on the graph. But you're welcome to do that. And you say from, A, capital A, I should say, is equal to 1/2 the acceleration. Okay, we also can get v naught, right? So v naught, that's 2.6. That units are meters per second. And we could say again that v is equal to v naught, and that's from our regression. Okay, and then same thing with the x naught, although we were able to get that already off of there. Anything else that we wanted to get that we weren't able to, let's say like v, for example, you could calculate, right? So for example, I could do maybe this equation. Right? Or I could use this equation. They'll give me the same value for v. For the velocity time graph, same idea here. I have one that has a regression model here on the right and one that does not here on the left. This should be a straight line. We know that because it should have a constant, the dog should have a constant acceleration associated with how its velocity is slowing over time. So it might be easier to try and figure out where the y-intercept to actually do a best fit line, right? This looks a little bit bumpy, right? So I'm going to go ahead and use this graph on the right because it has that best fit line. So I can see where it crosses, and it's about 2.5. Okay, again, the time we already had is 1.8. So that should be the same as what we had in the xt graph, right? So we can go over here and I can say this graph, because it has the same time axis as the other graph, right? The domain is going to be, again, 1.8. But the y-intercept of this graph is going to be when time is 0, what's the velocity? It's 2.6. So that means v naught is 2.6. Or I got 2.5, but I'm going to use 2.6 because that's what we got from the previous graph. I want you to be able to match those up. They should be the same within rounding. I can also get the ending speed v, right? So I'm just looking at the x and y axes. X-axis gave me time, y-axis gives me velocity, so I can get the beginning velocity and the ending velocity. Ending velocity is 0.45. It's not quite stopped, but it's pretty close. Okay, I can also look to the slope. Since this is linear, I can get the slope, and the slope is right here, right? So the slope here, this is going to be acceleration. We know the slope of a velocity time graph shows how the velocity is changing over time. And so that's going to be negative 1.2. You can see that this is the same value that we got from the position time graph. So there's overlap, but it's important to know how to get both of them. And if you have the choice between them, you can choose whichever one you like. If we look at the area under this graph, area is the new concept. I can't really get area under this because it's a curve, and it doesn't really give me anything to get area under it. Okay, like slope, we can figure out what area gives us by looking at what the units are. So for example, for steepness, rise, for an xt graph, it would be your change in position over time, right? This is your rise over your run for a position time graph, which was units of meters over seconds. For the velocity time graph, it would be your change in velocity over your change in time as your rise and run, which would mean that this is going to be meters per second per second. So therefore this slope is acceleration for your velocity time, and meters per second gave you velocity or speed for the position time graph. If we look at area, what we'd be doing is essentially taking base times height, so time times position, and that would give me units of meters times second, which is nothing. For a velocity time graph, we would be taking time times velocity, right? Base times height. And that's going to be a triangle. So I'm going to show you over here, and then we'll come back to the other page. So I'm looking at the area here and here. The total area between the 0 axis to our time and the change in velocity, our height. So I have base times height. Since this is triangular, I'm going to have to separate into two parts and add this triangle with this rectangle to get the total area. If we look at what the units give us, though, we're multiplying time in seconds times meters per second. So we multiply time, which is seconds, times meters per second. This gives us meters, which is delta x. So by doing area under the curve, I would be able to get the area. The area under the curve for the velocity time graph. I'd be able to get delta x. This may be tough for you to do because area is a new concept, but it oftentimes is easier than using the equations and having to go through and get all the variables if I can quickly do the area under a curve. For example, if this were all the way to 0, I would just do the triangular area, 1/2 base times height, and I would be able to get delta x that way. So after looking at the area here, I would have to take this height times the 1.8 base times 1/2 since it's a triangle, and then I would have to add that to the 0.45 height times the 1.8 base. And after doing that, you get 2.7. Okay, this actually is also in agreement with our previous graph's measure of 2.7. So if you're given both graphs, you may want to use just the range on your xt graph to get delta x, since you'd have to do area or an equation if you were going to be using your velocity time graph to get the same value. Again, if you were missing any of these, let's say you didn't do area, you could easily do the equation. For example, delta x is equal to 1/2 a t squared plus v naught t. And this is essentially going to give us the same thing because this is equivalent to the area underneath the curve. As long as you have the variables a, v naught, and t, you're able to solve for it. You can also use any other equation to get delta x as long as you have the other variables you would need to sub in and solve for it. To then complete the diagram that it's asking for, I'm going to draw muddy at the beginning and end. And I'm just going to start labeling these values. So my initial velocity was 2.6 meters per second. The ending velocity was much smaller, 0.45. Check that you have an arrow labeled with a letter, number, and units for each variable that has an arrow. Delta x, I'm going to switch colors. It would be measured from the middle of muddy from the beginning and end. So the delta x here is equal to 2.7 meters. Make sure that you have an arrow, it's not just a bracket. It should show direction. If we wanted to know x naught, this would be the beginning position of the tape measure, and x is the ending position on the tape measure. The acceleration we had is negative 1.2, so the fact that it's negative means it's going the opposite direction of the positive direction, right? Because it's going the negative direction. So negative 1.2 meters per second, or meters per second squared. And then the only other variable we have for the acceleration graph is the acceleration diagram, is going to be the time. And this does not require an arrow because there's no direction to time. And so this would be our diagram.